string theory, or trying to calculate the partition function of a conformal field theory on the torus, those things will become your good friends. Or if you just become an algebraic topologist. So actually, those four different classes of potential actually are the very famous, this is called a rational Calogero Moser system. And this is the trigonometric simply because it involves those trig function, or this will be for the complex y, that will be hyperbolic, but this will be a trigonometric Calogero-Moser system. And the last one will be the elliptic Calogero-Moser system. Unfortunately, I won't have time to talk about the kind of quantum mechanics, if you want, based on those class of Hamiltonian by promoting, for example, various momentum into operators and all that. So those systems not only exhibit classical integrability, which I'm going to show momentarily by showing you what the lax pairs for those guys are, and therefore you can construct all the commuting conserved charges, etc. But also, when you actually turn those classical conserved quantity into quantum mechanical operators, you can show that not only their Poisson bracket, so not only their classical Poisson bracket commutes, but also their quantum commutation relation. So, and that's actually covered in the beautiful review by those guys. So those four potential, and there's a fifth one, which is also very important. Because actually all these models we are talking about here actually play a very important, I guess they are the kind of simple harmonic oscillator for the high-energy theory people over the past 20 years. Which they are the models that we can actually know the exact spectrum, we can actually solve them, just like when you have the, your y-square potential, if you want. Okay. So the last one will be, I guess I call this, phi. Basically, when potential is equal to square exponential to qj minus qj plus 1. And the second one, which I call phi prime, is actually equal to j equal to n almost identical, but I make an additional identification of qn plus 1. So the last one, then that one after that last one, you come back to itself. So those two are also very famous potential. They are called basically non-periodic and periodic Toda system. So actually all these coefficients, in fact you might see like a different kind of ADE group classification of Toda system. But that is really just telling you that all this exponent here depends on different kind of classical Lie group of the weight of those guys in those entries. But otherwise, they are just given by a very simple potential of those form. And what's beautiful about this class of model is that, again, their lax pair can be explicitly constructed, and we can show that the system actually exhibits like classical integrability and so on. And what's even nicer about it, I'm just making those comments in passing now for those of you, who want to go on to do research in those topics, is that so if you actually promote those Hamiltonians, like classical Hamiltonian, into a quantum mechanical Hamiltonian, of course, the first thing, like what you do in quantum mechanics, that you'll be trying to find the eigenfunctions for those systems. It turns out that those eigenfunctions are actually very interesting type of polynomials. Something goes, it goes by the name of, they're different potentials. So for example, for the case of trigonometric, for the case for those class of potential, that usually you encounter some polynomial called the McDonald polynomial, or their simplification called Jack polynomial, which have played a rather prominent role in the context, in a different context of theoretical physics recently, and more prominently in something called topological strings. Actually, in fact, it also appear in various kind of other statistical models, like crystal melting and so on. So, anyway, so let me try to write a lax pair. That's what we need. So for the first four types of potential, go on, written over there. So just quick remind you what a lax matrix or lax equation actually look like. So we are trying to find some matrix equation, some explicit matrix which satisfy this type of relation, and the entries of in those matrix M and L are really functions of position and momentum of the system we are dealing with. And the point is that this equation is going to be equivalent to the Hamiltonian equations of motion. Okay, so it turns out that we can actually find the lax pair for these four different type of potentials by using the following ansatz that given by. So LJK simply indicates the entries in the matrix L. So this is given by Pj as a delta function or a unit matrix minus 1 delta Ik, sorry, Jk, and some coupling constant and some function. So the way to usually to solve this kind of relation is that you make a certain assumption, a certain ansatz that people usually say, and you plug it to your equation of motion you need to obey, and that gives you a constraint on what type of functions they should be, and then you solve the simpler equations. So minus I that's another function of so with the symmetries that x minus y equal to x y, and this is minus y. reflection symmetry for y to minus y, also for capital Y. Okay. So if we substitute those ansatz into your Lax equation, what you can see so those answers are usually the hard one to find out. They're based on, well, a lot of times educated guess and or like figuring out what are symmetries in your problem. So once you plug those things into the Lax equation, so you can solve for, you show that with the Vy, sorry, the Yy equal to minus x prime y and xy x prime omega minus so we will multiply them together, but with two different arguments together. We will obey the following equation. And finally, Ey is equal to x squared plus a constant, which you can interpret it. So Vy here is really a potential function you have. So the constant here, you can interpret it as where you actually measure your energy from. So usually we can set it to 0 or fix the value by initial conditions. So, sorry, let's solve. So the solution to this equation is simply given by the y equal to x double prime y over 2xy. So basically this tells you that once you specify your potential, then by taking square root, then you get a function xy, and you can from that obtain Vy and also your Zy. Okay, so we can write down for various cases. Like for example, the first one, your function xy is simply 1 for y, then you can deduce a lot of guys from those relations. And second one, xy equal to a over h y. Have a constant, and you can scale the constant by absorbing it into a, or if you don't have a constant, sin y. And similarly for other functions, fourth one, we give a a, where S is a Jacobi unit function. Hopefully some of you have seen it before when you do solving a pendulum. So, okay, so when you plug those in, then you can obtain all the Lax pairs, and from those the Lax matrix L, then you can construct all the conserved charges in your system. In fact, there are n of them, so I should represent JK here from 1 to n. So you have n degrees of freedom, and you have n conserved charges, and they all commute with each other, and so on and so forth. Then we show that those classical Hamiltonians are indeed trivial integrable. Okay, so and I think, let's see. Right, so I think I did similar in the notes for the TODA system, which for those of you interested, you can have a look. That step is very similar. The really hard one is actually trying to come up with the appropriate answers. The rest are just simple kind of algebraic manipulation. Okay, so at this point, I pretty much finished everything I want to say about classical integrability. So I don't know what you want to do. I mean, I can actually finish 15 minutes earlier today and just talk more 15 minutes tomorrow morning and to talk about all the quantum. I think that might be a better way for me also. How about that?